Hello, everybody. So now we are going to start with the answer of the question that we were asking the last video, which is how to determine or calculate the pressure under flow. So what we agreed on last time is, or we found last time, that the pressure is going to be scalar, meaning that it has no specific direction. It's affecting a point from all directions with the same magnitude. To be able to find this magnitude, we got this from some experimental results that we found that the pressure of the fluid or at a point under a fluid varies with depth. So the depth is the main parameter that affects it, and it can be easily explained that as the depth or the point gets deeper in a fluid, the weight of the fluid itself exerts more force or puts more pressure on the point. So as the point gets deeper, the pressure gets more due to the weight of the fluid. And to get this or get an equation that can describe this pressure variation with depth, we will do what we agreed on before, that we are going to take an element and do the calculations on, or do the derivation on. So let's say we have a fluid and there is or there are 2 points, point at height z1 and point at or at depth z1, and another point at a deeper point which is at z2, and the difference between the two depths is delta z. And we are going to, or we want to find the pressure difference between points P2 and P1. And of course, the pressure at point P2 is higher than the pressure at point P1 because it's deeper. So we want to find P2 minus P1. So to do this, we are going to have or do the calculations on a differential volume. It's a cube with dimensions dx, dy, and dz. And we're going to do the force balance as we did last time for the previous derivation. So we're only concerned with the vertical forces because we know that the depth is the only parameter that affects the pressure. And if we do the derivation on the horizontal direction, it's going to cancel out. So it's going to be the same force from both directions. So there is nothing that we can get out of this. So we're going to put the forces that we have. Of course, we know that there is a pressure on the top surface and there's a pressure on the bottom surface, which is slightly higher than the pressure on the top surface. So from the top surface, the pressure is going to be P. And from the bottom surface, it's P plus dP. So there is a very small change in the pressure, a differential pressure increase, because it's a differential volume. So the change in height is not big. So the change in pressure is going to be a differential pressure difference. And we're going to do the force balance. So the force balance in the z direction is going to be the pressure, the force due to pressure, which is the pressure times this area, which is dx dy, which is this area, and there is also the force due to the mass of this differential volume. So it's the volume dx dy dz multiplied by the rho times g, and this is rho g times dv, which is dx dy dz. And in the opposite direction, there is the pressure from the bottom, which is P plus dP times the area, which is dx dy. Okay. Now we can divide the whole equation by dx dy, so it's going to be P plus rho g dz minus P plus dP. The pressures will cancel out, and the equation is going to be dP equals rho g dz. Now we can do the integration from z1 to z2, or from z1 to z2. Of course, rho and g are going to be considered, g is constant, and rho can be considered constant if it's the same fluid. And now for the pressure is going to be P1 at Z1 and P2 at Z2. So it's going to be the integral of pressure from P1 to P2 and the height from Z1 to Z1 to Z2. And by doing the integration, this integration is going to be P2 minus P1, which is delta P, which is the change in pressure, and this is very important that what we are calculating here is the change in pressure, and we will come to this later, equals rho g times z2 minus z1, which is what we call here delta z. So in general, the equation can be written as the pressure at a point below is going to be the pressure at point above, which is at lower depth, plus rho g delta z. So this is the equation that we can use to calculate the pressure. The term delta z, sometimes it's referred to as the pressure head, which is the height that's causing the pressure. So there are some important notes. So this is the equation that we use. The equation is not used to calculate the pressure directly. It's used to calculate the change in pressure or the pressure at a point with the knowledge of the pressure at another point. And this is a very, very important thing, that you need to know, or we need to know the pressure at a point and use it in addition to the difference in height to get the pressure at another point, at another elevation. Okay, so one of the very, very common cases that if we have the surface or the known pressure is the pressure at the surface of a liquid. And this surface is open to the atmosphere, so the pressure here is atmospheric pressure. So the pressure at point P is going to be the atmospheric pressure plus rho gh. Okay, this is the absolute pressure. If it's the gauge pressure, it's going to be rho gh only. Okay, so this is like a common case that we deal with a lot, to have a fluid or to calculate the pressure in a fluid whose surface is exposed to the atmospheric pressure. From the same equation here, if there are 2 points that are at the same elevation, meaning that delta z or delta z is 0, then the pressure is the same. And this is a very, very intuitive thing, that 2 points, and we can take it as a rule, that 2 points at the same elevation in the same fluid will have, or at the same depth, I'm sorry, at the same depth in the same fluid will have the same pressure. Okay. The last thing is that the pressure increases linearly with the depth, or the increase in depth. So if it increases by 1 atmosphere with, let's say, or 1 kilopascal with 10 centimeter, then it's going to be 2 kilopascal with 2 centimeter depth, and 3 kilopascal and 30 centimeter depth, and so on. So this is a linear increase. There is one other important thing here, is that the pressure is not only dependent on the depth, and we will go back to the equation, it's also dependent on the density. The density has a very important effect on the pressure. So we'll take 2 cases for 2 very common fluids, which is air and water. We know that the density of water is around 1000 kilogram per meter cube, and air is 1.2 kilogram per meter cube. So if we want to calculate the change in pressure due to depth of 100 meter for both fluids, if we do the calculations, you'd see here that it's rho gh. This is the delta P for water and delta P for air. So the number here and number here, there is like 3 orders of magnitude. This is almost 10 power 6, and this is almost 10 power 3. So it's 1000 times more pressure difference, just because of the density. Although it's the same depth, but it has a very, very big impact on the pressure. That's why it makes a lot of difference for different fluids. One last thing here, which is a very, very nice thing. This is a figure for a container that contains water. Let's say it's an ocean or a sea or whatever, but the bottom surface of this water container is not smooth, or it's not flat. So there are hills and troughs, and there are difference in heights here. There are some points that are highlighted here: point A, B, C, D, E, F, G, H, and I. Although the point A, B, C, D, and E, and F, and G, all these 6 points are not on the same flat surface, but they are all at the same elevation or at the same depth for in the same connected fluid. So the points A, B, C, D, E, F, G all have the same pressure. They have the same pressure because it's the same depth in the same connected fluid, and this is very important, that the fluid has to be connected, meaning that there is a route from point A to point B in the same fluid, and a route from B to C, from C to D, and so on. Okay. However, for points H and I, they are at the same depth, but it's different fluids. There is mercury here, so the pressure here is not going to be the same as the pressure here because it's not the same fluid. So this is a very good example to have a visual understanding of the height and how it affects the pressure, and it has to be in the same fluid to say that it's the same pressure. Starting from next video, we will start with applications, and this is one of the very useful things that will give us a good understanding of why what we are studying here is important. There are a lot of applications that depend on the concepts that we covered, and this is what we are going to start with next time, inshallah. So, see you then, inshallah.